The International Space Station, ISS, is a large, habitable space facility orbiting Earth. Here's a detailed explanation of what it is, structure and size. The ISS is modular, constructed from various components launched and assembled in space. It's about the size of a football field, measuring 109 meters long and 75 meters wide. The pressurized volume is approximately 916 cubic meters, comparable to a 6-bedroom house. Orbit and speed: it orbits Earth at an average altitude of about 400 kilometers, 250 miles. The ISS completes an orbit around Earth every 92 minutes, traveling at about 28,000 kilometers per hour, 17,500 miles per hour. Purpose: serves as a microgravity and space environment research laboratory, conducts experiments in biology, physics, astronomy, meteorology, and other fields, tests spacecraft systems and equipment for future space exploration missions, provides a platform for Earth observation and space environment studies. International collaboration: a joint project involving 5 space agencies: NASA, USA, Roscosmos, Russia, JAXA, Japan, ESA, Europe, and CSA, Canada. Crews from various nations live and work on the station. Construction and maintenance: assembly began in 1998 and was largely completed by 2011, though modules continue to be added. Requires regular resupply missions and maintenance. Life support systems: generates oxygen through electrolysis of water. Recycles water from various sources, including urine. Maintains atmospheric pressure similar to Earth's sea level. Powered by an acre of solar panels that convert sunlight to electricity. Scientific achievements: has hosted over 3,000 research investigations from researchers in more than 100 countries. Contributes to advancements in health, telemedicine, education, and Earth observation. Crew typically hosts 6 to 7 crew members at a time. Crew members usually stay for about 6 months. Future: expected to operate until at least 2030. Serving as a test for technologies needed for deep space exploration. The International Space Station, ISS, has been a hub for scientific research and discovery since its inception. Here's a detailed overview of some key discoveries and areas of research. 1. Human health and space medicine. Effects of microgravity on the human body. Bone and muscle loss. Studies have shown significant bone and muscle atrophy in astronauts, leading to improved exercise regimens and countermeasures. Fluid shifts. Research on how bodily fluids redistribute in microgravity, affecting vision and intracranial pressure. Space radiation effects. Ongoing studies on radiation exposure and its long-term impacts. Telomere research. Surprising findings that telomeres, protective end caps of chromosomes, lengthened in space. 2. Biology and biotechnology. Protein crystal growth. Microgravity allows for larger, more perfect crystals, aiding in drug development. Plant growth studies. Discoveries about how plants adapt to space, crucial for future long-duration missions. Microorganism behavior. Studies on how bacteria and other microorganisms evolve in space. 3. Physical sciences. Fluid dynamics. New insights into how fluids behave without gravity, applicable to engineering and medicine. Combustion science. Studies on how fire behaves in microgravity, improving fire safety in space and on Earth. Material science. Research on metal alloys and other materials formed in microgravity. For Earth and space science: Earth observation, detailed monitoring of climate change, natural disasters, and urban development. Cosmic ray detection. The alpha magnetic spectrometer has provided new data on cosmic rays and dark matter. Atmospheric studies. Research on the upper atmosphere and its interaction with space. 5. Technology development. 3D printing in space, successfully demonstrated, opening possibilities for on-demand manufacturing in space. Water recycling systems. Advanced recycling technologies developed for space now applied on Earth. Robotic assistance. Testing of free-flying robots to assist astronauts. 6. Educational outreach. Student experiments. Numerous experiments designed by students have been conducted, fostering STEM education. 7. Dark matter research. The alpha magnetic spectrometer has collected data that may help in understanding dark matter and antimatter. 8. Exoplanet detection. The TESS telescope, while not on the ISS, has utilized ISS for calibration and has discovered numerous exoplanets. 9. Cold Atom Lab. Created the coldest known place in the universe, studying quantum effects at extremely low temperatures. 10. Tissue chip research. Studies using organs on chips to model human physiology in space, with implications Applications for drug development. 11. Advanced colloids experiment, research on the behavior of colloids in microgravity, with applications in materials science. 12. Rodent research, studies on mice have provided insights into muscle and bone loss, and potential treatments. These discoveries have wide-ranging implications, from improving life on Earth to preparing for long-duration space missions. The ISS continues to serve as a unique laboratory, enabling research that's impossible to conduct on Earth. The International Space Station, ISS, has played a crucial role in the search for dark matter, primarily through the Alpha Magnetic Spectrometer (AMS-02) experiment. Here's a detailed explanation of how the ISS has contributed to this search. 1. Alpha Magnetic Spectrometer (AMS-02) installation. The AMS-02 was installed on the ISS in May 2011 during the STS-134 mission. Purpose: it's designed to search for various types of unusual matter by measuring cosmic rays. Size and cost: it weighs 7.5 tons and cost approximately $2 billion to develop. 2. How AMS-02 works. Particle detection: it detects charged particles passing through its layers of detectors. Magnetic field: a strong magnet bends the paths of these particles, allowing measurement of their charge and momentum. Particle identification: various detectors identify the type of each particle passing through. 3. Dark matter search strategy, indirect detection. AMS-02 doesn't directly detect dark matter but looks for its decay or annihilation products. Focus on antimatter: it particularly searches for positrons and antiprotons, which could be produced by dark matter interactions. For key findings: positron excess. AMS-02 has observed an excess of high-energy positrons, which could be a signature of dark matter. Precise measurements: it has provided the most accurate measurements of cosmic ray spectra to date. Antihelium detection: potential detection of antihelium nuclei, which could have implications for dark matter theories. 5. Advantages of space-based detection: no atmospheric interference. Being above Earth's atmosphere allows for cleaner, more accurate measurements. Continuous operation: the ISS provides a stable platform for long-term data collection. Large acceptance: its position allows it to observe a large portion of the sky. 6. Collaboration and data analysis, international effort. The AMS collaboration involves 56 institutes from 16 countries. Data processing: huge amounts of data are transmitted to Earth for analysis. 7. Implications for dark matter theories, constraining models. The data helps to constrain or eliminate certain dark matter models. New possibilities: it has opened up new avenues for dark matter research and theories. 8. Challenges and upgrades, cooling system repair. In 2020, astronauts performed complex spacewalks to repair the AMS-02's cooling system, extending its operational life. 9. Complementary research: while not directly related to the AMS-02, other ISS experiments contribute to our understanding of fundamental physics, indirectly supporting dark matter research. 10. Future prospects, continued operation. The AMS-02 is expected to continue collecting data until the end of the ISS mission. Potential discoveries: with more data, there's hope for breakthrough discoveries in dark matter physics. 11. Educational impact: the AMS-02 project has also served as an educational tool, inspiring students and researchers in particle physics and cosmology. While the AMS-02 hasn't definitively discovered dark matter, it has significantly advanced our understanding of cosmic rays and provided valuable data that constrains dark matter theories. The ISS's role in hosting this experiment has been crucial in pushing the boundaries of our knowledge about the universe's composition. The International Space Station, ISS, is a complex, multifaceted system. Here's a detailed explanation of how it works. 1. Structure and components. Modules: the ISS consists of various pressurized modules, each serving specific functions: living quarters, laboratories, docking ports, etc. Truss: a long backbone-like structure supports solar arrays and radiators. Solar arrays: large panels that convert sunlight into electricity. Robotic arms: used for maintenance, docking assistance, and experiments. 2. Orbital mechanics. Altitude: orbits at about 400 kilometers above Earth's surface. Speed: travels at approximately 28,000 kilometers per hour, completing an orbit every 92 minutes. Orbital adjustments: periodic boosts are needed to maintain altitude due to atmospheric drag. 3. Life support systems. Oxygen generation: uses electrolysis to split water into oxygen and hydrogen. Carbon dioxide removal: utilizes various methods including lithium hydroxide canisters and a molecular sieve system. Water recycling: reclaims water from urine, sweat, and condensation. Temperature control, a complex system of heat exchangers and radiators maintains habitable temperatures. For power systems, solar power, primary source of electricity. Batteries, store power for use when the station is in Earth's shadow. Power management, distributes electricity to various systems and experiments. 5 are communication systems, S-band, for audio and basic telemetry. Ku-band, for high-rate data transmission and video. GPS, for precise orbital tracking. 6. Propulsion and attitude control, Russian thrusters, used for major orbital adjustments. Control moment gyroscopes, for attitude control and fine positioning. 7. The docking and berthing, various ports allow spacecraft to dock or be berthed by the station's robotic arm. Supports both Russian and US/international vehicle docking systems. 8. Scientific facilities, multiple research racks and external platforms for various scientific experiments. Specialized equipment for microgravity research in biology, physics, astronomy, and material science. 9. Crew systems, living quarters, sleep stations, hygiene facilities, exercise equipment. Galley, for food preparation and dining. Waste management, specialized toilets designed for microgravity use. 10. Environmental control, air pressure, maintained at sea level pressure, 101.3 kPa. Fire detection and suppression, specialized systems designed for the space environment. 11. Radiation protection, the station's structure provides some shielding. Crew exposure is carefully monitored. 12. Debris protection, Whipple shields protect against micrometeorites and orbital debris. 13. Resupply and maintenance, regular cargo missions bring supplies, experiments, and replacement parts. Astronauts perform routine and emergency maintenance, sometimes requiring spacewalks. 14. Command and data handling, multiple computer systems control various aspects of station operations. Ground control teams in multiple countries monitor and assist with operations. 15. Emergency systems, escape vehicles, Soyuz capsules, are always docked for emergency evacuation. Redundant critical systems ensure safety and continuity of operations. The ISS functions as a result of the intricate interplay between these systems, international cooperation, and constant monitoring and maintenance. It's a testament to human engineering and collaboration, operating as a self-contained outpost in the harsh environment of low Earth orbit. The International Space Station, ISS, has been a hub for numerous important scientific discoveries across various fields. Here are some of the most significant discoveries and advancements made on the ISS. 1. Human health and space medicine, bone and muscle loss countermeasures, discovery. Astronauts lose bone and muscle mass at an accelerated rate in microgravity. Importance, led to the development of specialized exercise regimens and medical treatments, with applications for osteoporosis patients on Earth. Telomere elongation, discovery, astronauts' telomeres, protective ends of chromosomes, lengthen during spaceflight. Importance, provides insights into aging and cellular health, potentially leading to new therapies. Fluid shifts and space syndrome, discovery, microgravity causes bodily fluids to shift upwards, affecting vision and intracranial pressure. Importance, critical for planning long-duration space missions and understanding related conditions on Earth. 2. Microbiology, bacterial mutation rates, discovery, bacteria mutate faster in space. Importance, crucial for understanding disease progression and antibiotic resistance in space and on Earth. 3. Physics and material science, cool flames, discovery, observation of cool flames that burn at lower temperatures than possible on Earth. Importance, could lead to more efficient engines and better fire safety. Bose-Einstein condensates, discovery, creation of Bose-Einstein condensates in space. Importance, allows for more precise study of quantum physics phenomena. For Earth and space science, cosmic ray detection, discovery, the alpha magnetic spectrometer has provided new data on cosmic rays and antimatter. Importance, contributes to our understanding of the universe's composition and the search for dark matter. Lightning and atmospheric phenomena, discovery, observation of sprites, jets, and elves, upper atmospheric lightning. Importance, improves our understanding of Earth's atmosphere and global electric circuit. 5. Plant biology, plant growth in microgravity, discovery, plants can grow in space with modified behaviors. Importance, critical for future long-duration space missions and potential space colonization. 6. Protein crystal growth, improved crystallization, discovery, protein crystals grow larger and more uniformly in microgravity. Importance, allows for better structural analysis, aiding in drug development. 7. Fluid dynamics, capillary flow, discovery, new insights into how fluids move in microgravity. Importance, applications in designing better life support systems and managing fluids in space. 8. Technology development, 3D printing in space, discovery, successful demonstration of 3D printing in microgravity. Importance, opens possibilities for on-demand manufacturing in space. 9. Dark matter research, potential dark matter signatures, discovery. The AMS-02 experiment has observed unexplained positron excess. Importance, could be a signature of dark matter, contributing to fundamental physics. 10. Exoplanet research, while not directly on the ISS, the station has supported missions like TESS, Transiting Exoplanet Survey Satellite, by providing a platform for calibration. These discoveries have wide-ranging implications, from improving life on Earth to preparing for long-duration space missions and expanding our understanding of the universe. The ISS continues to serve as a unique laboratory, enabling research that's impossible to conduct on Earth due to the presence of gravity. It's worth noting that the importance of many ISS discoveries lies not just in individual findings, but in the cumulative knowledge gained about living and working in space, which is crucial for future space exploration. The International Space Station, ISS, uses a complex system of thrusters for maintaining its orbit, attitude control, and making necessary adjustments. Here's a detailed explanation of how the ISS thrusters work. 1. Types of thrusters. A. Russian segment thrusters. Primary thrusters are located on the Zvezda service module and Progress cargo ships. These are responsible for major orbital adjustments and reboosts. B. US segment thrusters. Smaller thrusters on various modules for fine attitude control. 2. Propulsion systems. A. Main propulsion system, located on the Zvezda module. Uses hypergolic propellants, unsymmetrical dimethylhydrazine, UDMH, as fuel and nitrogen tetroxide, N2O4, as oxidizer. These propellants ignite on contact, eliminating the need for an ignition system. B. Reaction control system, RCS, smaller thrusters for attitude control and minor adjustments. Also uses hypergolic propellants. 3. Thruster operation. A. Combustion. When fired, the fuel and oxidizer mix and combust in the combustion chamber. This creates high-pressure, high-temperature exhaust gases. B. Exhaust. The hot gases are expelled through a nozzle at high velocity. This expulsion creates thrust based on Newton's third law of motion. 4. Thrust levels. Main thrusters on Zvezda, approximately 3000 N, 670 lbf each. Smaller attitude control thrusters range from 130 N to 290 N, 29 to 65 lbf. 5. At control and coordination, thrusters are controlled by the station's onboard computers. Ground control can also command thruster firings when needed. The system coordinates multiple thrusters to achieve desired movements. 6. Usage scenarios. A. Orbit raising, periodic reboosts to counteract atmospheric drag. Typically performed using Progress cargo ship thrusters or Zvezda's main engines. B. Collision avoidance, quick firings to move the station away from potential orbital debris. C. Attitude control, maintaining proper orientation for solar panels, thermal control, and communications. D. Docking support, fine adjustments during spacecraft approach and docking procedures. 7. Fuel management, propellants are regularly resupplied by Progress cargo ships. Careful fuel budgeting is essential for long-term station operations. 8. Environmental considerations, thruster firings are planned to minimize impact on microgravity experiments. Exhaust plumes are directed to avoid contamination of solar arrays and other sensitive equipment. 9. Redundancy and safety, multiple thruster systems provide redundancy for critical operations. Fail-safe mechanisms prevent accidental firings. 10. Future developments, exploration of more efficient propulsion systems for future space stations and deep space missions. Potential integration of electric propulsion for long-term station keeping. The ISS thruster system is a critical component of the station's operations, ensuring its continued presence in low Earth orbit and enabling it to serve as a platform for scientific research and international cooperation in space. The creation of the International Space Station, ISS, was a complex process that spanned several years. Here's a detailed explanation of how and when the ISS was created. 1. Conceptual origins. 1984, President Reagan proposes Space Station Freedom as a US-led project. 1993, the Clinton administration redesigns the project to include Russia, leading to the ISS concept. 2. International cooperation. 1998, the Intergovernmental Agreement on Space Station Cooperation is signed by 15 countries. Main partners: NASA, USA, Roscosmos, Russia, ESA, Europe, JAXA, Japan, and CSA, Canada. 3. Construction timeline. A. 1998, launch of first modules, the 20th of November, Zeroya, functional cargo block, launched by Russia. December the 4th, Unity node, Node 1, launched by NASA, connected to Zeroya. B. 2000, key additions, July, Zvezda service module launched, providing living quarters and propulsion. C. 2000 to 2001, initial systems and solar arrays, expansion of power systems and addition of the Destiny laboratory. D. 2001 to 2007, continued expansion, addition of airlocks, trusses, and solar arrays. European and Japanese laboratories prepared for launch. E. 2008, European Columbus laboratory added. F. 2009, final set of solar arrays installed, completing the main power system. G. 2010 to 2011, completion of major construction, Japanese Kibo laboratory fully assembled. Final major US components added. H. 2016 to 2021, addition of inflatable beam module and new docking adapters. For construction challenges, over 40 assembly flights were required. Involved complex spacewalks and robotic operations. Coordinated efforts between multiple space agencies and launch systems. 5. A key milestones. The 2nd of November 2000, first long-term crew, Expedition 1, arrives. The 7th of February 2001, Destiny Lab module allows for expanded scientific research. 2010, all major modules are in place, marking substantial completion. 6. Technological innovations, development of new spacewalking techniques, advancements in robotic arm technology, improvements in life support systems. 7. Funding and costs, estimated total cost, over $150 billion through 2020. Costs shared among participating nations based on their contributions. 8. Continuous evolution, the ISS continues to evolve with new modules and capabilities added over time. Recent additions include the Nauka module 2021 and new solar arrays 2021 to 2023. 9. Operational status, continuously occupied since November 2000. Currently approved to operate until at least 2030. 10. Legacy and future, serves as a model for international cooperation in space. Informs designs and plans for future space stations and deep space habitats. The creation of the ISS represents one of the most complex and ambitious international scientific and engineering projects ever undertaken. It showcases the power of global cooperation in achieving monumental goals in space exploration and scientific research. That was all. Goodbye.